Yay.
Yay!
Did we just work on the project?
Yep, we're working on our project. Has everybody been taking their readings?
Heck yeah.
Did y'all get them last night? This is the last week.
We got our last one yesterday.
Next week, we're going to be working on the project all week.
We got a really high dissolved oxygen.
Really?
Yeah, it went from 4 to 8.
Sweet.
Do you hear things are going to be weird?
Cool results. Maybe there was some sort of mixing or something going on.
Yeah, Bridget says that's something to do with the cold.
With the cold? Well, colder water does hold more oxygen.
Good effort.
Interesting. Do it, Bridget. All right. This chapter is an important chapter. This talks about all the problems our oceans are facing, and it's something that you're going to have to deal with your whole life. Especially if you live on the ocean, like we do now, your problems are closer to home for you than anyone else. Now, this is something that our oceans are facing and our land is facing. It's called global warming. Have you heard of that?
Yes.
This is a graph showing the global temperature for the last 130 years. And as you can see, it's going up. And why it does that, we have figured out. First, they weren't sure. But now we know it's increased carbon dioxide in the air. So one of the main gases in the air that holds heat is carbon dioxide. There's a few gases that hold heat in the air. Methane, water. If you got more water in the air, it holds more heat. But carbon dioxide is the one that's changing a lot. It's going up. Why is carbon dioxide going up? Because whenever you burn something, the gas that's produced is carbon dioxide. And that goes into the air. It makes the air thick. If we take these trees that are around here and we burn them, we'll fill the air with more carbon dioxide. Is that happening on the Earth? Yes, it is. Whenever they clear cut a place to build something new, you cut all the trees, and they either bury them or burn them. In either way, or so they use some of it as wood, but only about 5% of the trees that are cut are used as wood to build things. The rest is either burned or buried, and even when you bury it, it decomposes, and the carbon dioxide ends up going in the air. It's just, if you bury it, it turns out it's just like if you burn it, it decomposes, the carbon dioxide ends up in the air. And that's what causes the temperature to go up. This is a graph showing the carbon dioxide levels over the same time period. Carbon dioxide levels have gone up. Temperature has gone up. Simple as that. Now, what's scary to a lot of people about this is a graph of carbon dioxide levels over the last 1,000,000 years. How do they know this? They can get it from ice core samples. It's actually, this is 800,000 years. They can take ice cores. They can go in the ice wherever there's ice, like in a glacier or in Antarctica. They can drill down in the ice, and the ice preserves when the snow falls. The CO2 gets locked into the snowfall. And so the different layers of snow over the last 800,000 years has trapped the carbon dioxide. So you can check what the carbon dioxide was like 800,000 years ago if you drill down that far into the ice. Tony, are you with me here?
I'm with you.
This is incredible stuff. And so this is a graph of carbon dioxide levels over the last 800,000 years. Where it goes up, that's when the temperature on the Earth was high. Where it goes down, that's when the temperature on the Earth was cold. We call these low spots ice ages. There was an ice age 750,000 years ago. There was another one 650,000 years ago. There was a little bit of one 550,000 years ago. About every 100,000 years you get an ice age. Those are times when carbon dioxide levels are low. So there is a natural variation in the carbon dioxide levels on Earth. It goes up and down naturally. So where is the carbon dioxide now? Follow this line if you can with me. Here's what it's done. Bam. That's where it is right now. That's what we've done in the last 100 years. That's the line. That's what's happened to carbon dioxide levels in the last 100 years. That's what's making people nervous. Look at the rate of increase over what it's been for almost 1 million years. Way above. Keep in mind that the low point here causes an ice age. It changes Earth that dramatically. Going down in carbon dioxide that much is a dramatic change on our planet. That's the polar ice cap stretching all the way down into New York City, going down in carbon dioxide that much. Look how much up we've gone in carbon dioxide. That's why people are nervous about global warming. The temperature usually lags behind the carbon dioxide levels. So the carbon dioxide levels will go up first, and then the temperatures will follow after. And carbon dioxide levels are already there. But if we don't do anything about it, you know where it'll be in the next 100 years?
Twice that.
Double that. Way up here. What's that going to do? We don't know.
Kill us all.
Because we haven't had anything like that in 1 million years on the Earth. We don't know what it's going to do. So people are nervous about it. So what's the way around that? Is there any way to stop it? Well,
Ride your bike.
stop burning so much stuff. How do you stop burning so much stuff? Maybe have other ways of creating electricity other than fossil fuels. There are ways to create electricity other than burning fuel. You can use solar. You can use nuclear. You can use water power. Hydroelectric. Solar is getting real big right now. They're putting up
Isn't
some solar farms.
harder though?
It's not quite as nice as it's not quite as easy as just burning coal.
Yeah.
Burning coal and burning natural gas is easy. We got a lot of it. We can pump it out of the ground and we can burn it. But it doesn't do anything to stop this line.
You use wind too, right?
You can use wind. A lot of places are using wind. Denmark gets most of its energy from wind.
Where's Denmark?
It's over there in Europe.
Asia.
So you guys are going to have to be, and me too, we're going to have to be dealing with this the rest of our lives. One of the things, I'll show you some of the problems with this. Yeah.
I was just going to ask, is there, other than the temperature going up, is there any way having that much carbon dioxide could kind of screw everything up, other than just bring the temperature
Yes,
up?
let's look at some of the things.
Would it
Other than the temperature. First of all, here's where the temperature actually changes the most near the Arctic Circle up north. And that's because it melts all the ice that is on the ocean up there. And when that ice melts, it heats the ocean up there. Right now, the ice is reflecting sunlight. But if that ice melts, the ocean is a lot darker than ice and will absorb the sunlight. And so you get the biggest rise in temperature in the northern part of the planet. So that's where it's predicted to rise in the Arctic in the next 50 years or so by about 10 degrees, 10 or 15 degrees. It's not going to rise so much where we are, but it's going to rise a lot up there. It's going to end up melting all the ice is what's going to happen. And what is that? Is that a problem for us? Yeah, because if you melt all that ice up there, the water levels go, the ocean levels go up. If we were to lose all the ice in Greenland alone, that'll raise the ocean levels 20 feet. The entire island will be underwater. The highest point on this island is like 12 feet. So that is a problem for us in Florida and anything else near the coast. Let's watch this quick video on global warming, and then we'll talk about what your question was asking.
The Earth's climate has fluctuated, cycling from ice ages to warmer periods. But in the last century, the planet's temperature has risen unusually fast, about 1.2 to 1.4 degrees Fahrenheit. Scientists believe it's human activity that's driving the temperatures up, a process known as global warming. Ever since the Industrial Revolution began, factories, power plants, and eventually cars have burned fossil fuels such as oil and coal, releasing huge amounts of carbon dioxide and other gases into the atmosphere. These greenhouse gases trap heat near the Earth through a naturally occurring process called the greenhouse effect. The greenhouse effect begins with the sun and the energy it radiates to the Earth. The Earth and the atmosphere absorb some of this energy, while the rest is radiated back into space. Naturally occurring gases in the atmosphere trap some of this energy and reflect it back, warming the Earth. Scientists now believe that the greenhouse effect is being intensified by the extra greenhouse gases that humans have released. Evidence for global warming includes a recent string of very warm years. Scientists report that 1998 was the warmest year in measured history, with 2005 coming in second. Meanwhile, readings taken from ice cores show that the greenhouse gases carbon dioxide and methane have hit their highest levels in the past 420,000 years. Arctic sea ice is also shrinking. According to NASA studies, the extent of Arctic sea ice has declined about 10% in the last 30 years. As long as industrialized nations consume energy and developing countries increase their fossil fuel consumption, the concentration of greenhouse gases in the atmosphere will continue to rise. Researchers predict that temperatures will increase about 2 to 10 degrees Fahrenheit by the end of the century. What's less certain is what rising temperatures mean for the planet. Some climate models predict subtle changes. Others forecast rising sea levels which could flood coastal areas around the world. Weather patterns could change, making hurricanes more frequent. Severe droughts could become more common in warm areas, and species unable to adapt to the changing conditions would face extinction. Although much remains to be learned about global warming, many organizations advocate cutting greenhouse gas emissions to reduce the impact of global warming. Consumers can help by saving energy around the house, switching to compact fluorescent light bulbs, and driving fewer miles in the car each week. These simple changes may help keep the Earth cooler in the future.
It's a tough problem.
Yeah.
Tough problem to figure out. So we're going to have to deal with that our whole lives thinking about it. Believe it or not, global warming is already killing hundreds of thousands of people a year.
People?
People.
How?
Here's how. The temperature's gone up a couple degrees. And what that's done is allowed the mosquito to increase its range. Mosquitoes are normally tropical. They like it warm. But because of that, just a couple degrees, they spread out into more areas of the globe, and they've brought malaria with them. Have you ever heard of that disease?
I have.
And malaria kills millions of people a year. It's the biggest disease in the world. We're lucky we don't have it here. You know why we don't have it here? It's too cold here.
Is it worse than like AIDS?
Yes. Kills more than AIDS.
HIV. Yeah.
Kills more than HIV. Yep. So we're lucky because it's too cold for malaria here. Because the mosquito that carries malaria isn't up here yet. But guess what? It's really close now. It was just in Central America, and it's moved up, and it's getting up into higher up into Mexico. And if it keeps getting warmer, we're going to have malaria here in the United States.
Isn't there a vaccine?
They're working on a vaccine for it, but it's not perfectly successful yet. They're working on it.
So just getting bit by a mosquito?
If you get bit by a mosquito that was carrying that disease, you would get it. And it only kills a couple percent of the people that are infected, but so many people are infected that translates into millions.
Didn't we have like
Millions dead.
West Nile here or something like that? Ebola?
I don't know. That's a less common killer, but yeah, that's bad. I don't know if West Nile was here. Maybe it was.
It was in the wick.
Was it? So let's talk about, Charlie, you're asking, is there any other effects? Yes, there is. And one of them is rising lowering the pH of the ocean. Because the water in the ocean absorbs a lot of the CO2. So the carbon dioxide doesn't just go into the air, it goes into the water. And in the water, it combines with H2O to form carbonic acid. CO2 plus H2O makes carbonic acid. And carbonic acid is an acid, and it lowers the pH of the ocean. So the entire ocean pH has gone down. This is showing where the pH change is the biggest. We've had a pretty good amount of pH change right near us. Around, gone down about 0.08, and you might not think that's much, but that's enough to kill coral. We're at the base of the food chain in the ocean. A lot of coral are very pH sensitive. And just a tiny move in pH, they can't survive. And especially one thing that it does is it eats up the shells of the coral. And not just the shells of the coral, the shells of all the mollusks too.
With dissolves in it?
Like snail shells and clam shells and oyster shells. A lower pH causes their shells to be thinner and more brittle, and so they die easier because they don't have as much protection. So this is a big problem. Causes massive coral bleaching. Have you ever heard of that?
Mm-hmm.
The guy in Hawaii talked about that. What's that?
And that would happen to the Great Barrier Reef.
That's right. A lot of the Great Barrier Reef has bleached. That means the coral's dead, and all that's left is their shells.
Good job, Willie. Welcome,
So we call this whole problem ocean acidification, and it's also from CO2. And now, if there's not enough coral, then there's nothing eating the coral, so you lose your fish. Because the coral is at the bottom of the food chain. Let's see video footage on that.
By now you've heard that the way we're living is filling up our atmosphere with carbon dioxide. As a result, the planet's warming. Heat waves and floods are more likely to be extreme, and people's lives will get tougher. And the more we learn about climate change, the more risks we uncover. Since we started burning fossil fuels, the ocean has absorbed about half of all the CO2 we humans have put out. That's why it's called the planet's biggest carbon sink. Now this is good because it's kept a lot of CO2 out of the atmosphere. But as the ocean warms, it takes up less and less CO2. And with all that CO2 in the sea, scientists are shedding light on, well, an ocean of problems. Ready for the first big problem? Some sea creatures like clams, oysters, and coral, their shells and skeletons are getting weaker. Okay, you've got bigger problems than easy-to-crack clams? Maybe not if you're among the 1 in 7 people who get most of their protein from seafood. Or if you understand how unstable the world would be with 1 billion more hungry people. What's weakening the shells? Well, these little creatures are going about their lives scooping up molecules called carbonate ions to be the building blocks of their shells. But when CO2 reacts with seawater, it releases hydrogen ions, which compete with shells for carbonate. With more hydrogen ions floating around in the ocean, our little friends have to spend more energy building their shells and have less energy for finding food. That means it's harder to grow, and more will die off before they get big. So the fish that eat the clams or live among the coral will have a harder time surviving, meaning the fish that dine on them won't have enough to eat, and so we won't have enough to eat. Remember those pesky hydrogen ions generated by more CO2? They don't just take away the carbonate ions that these little clams need, they also make the ocean more acidic. It's already become 30% more acidic since we started spewing all this CO2, and it could get much worse. We could change the ocean's chemistry so much that shells actually start to dissolve. That means if we don't turn this problem around, your great-grandkids might think of reefs the way you think of a dodo bird. And with 1 in 4 ocean species living in coral reef ecosystems, weaker coral could threaten the foundation of the whole ocean food chain. But why panic, right? Life always seems to find a way to adapt, but it needs time. In a few decades, we might make the oceans more acidic than they've been in 20 million years. It's hard to imagine any ecosystem quickly adapting to that big of a change. But things don't have to get that bad. We've started this problem, and we're going to fix it, beginning at its source, carbon dioxide from burning fossil fuels. Learn more at acespace.org.
That's pretty good.
I like the music.
Yeah, that's well done.
Was it lit?
Really good.
What other problems are there? Well, there's pollution. Y'all know about pollution. Trash in the water.
Oh well.
Did you know there's just a giant mass of plastic floating in the middle of every gyre? Remember those big gyres, those big circular currents that are moving in every ocean?
Mm-hmm.
At the center of those is a big, just a bunch of plastic trash just floating around from what people have thrown in the oceans. It's a giant center of pollution.
Where's that at right there?
I don't know where that is. There's a lot of pollution.
Indonesia.
Most of the pollution, though, that's really bad for ocean organisms isn't big pieces of plastic. It's the tiny little chemicals that come from the pollution that we release that get in the water and affect these organisms. And have you ever heard of mercury poisoning?
Mm-hmm.
There was a big problem with mercury poisoning. Companies were dumping just mercury that's used in a lot of processes and factories and stuff. They were just releasing it into the waters. It was getting into the seafood. And there's a process called biological magnification where it gets in the little plants, all this mercury gets in the little plants, and then fish eat the plants, bigger fish eat the little fish, and it works its way up the food chain and becomes very concentrated in the organisms at the top of the food chain, which are the fish that we like to eat, the big fish. You catch a big fish like a tuna and you eat it. Well, if it's got a bunch of mercury in it, you can become poisoned. And there was a lot of problems with mercury poisoning before we figured out, hey, we need to stop these polluters. And we started to put a bunch of laws in place saying you couldn't pollute, you couldn't just release mercury into the water, and the problem's gotten better in that respect. But pollution can still be a problem. So there's a lot of marine pollution out there, and you gotta control. People don't like too much government, but you have to. If you just let people do whatever they want, you can affect the health of everyone. Kill all the organisms. We don't want that.
Chevrolet is the most rewarded car company in the last 2 years.
No way.
We're waiting on this one.
How much trash is in the ocean?
This fierce.
Chevy's coming out. Some nice stuff.
Every time we think we found a piece of the lost plane, it turns out to be giant ocean trash. How much trash is in the ocean? Anthony Carboni here for D-News, and the search for Flight 370 is unearthing huge amounts of debris. Over 4 hours, a single search plane from New Zealand spotted 70 objects they thought could have been from the plane, but it turned out to be things like huge tangles of fishing line and icebox lids. A French satellite spotted a 75-foot-long object they thought could be a wing from the plane, but it turned out to be scrap that could have been anything from a piece of an old shipping container to an overturned yacht hull to a rocket booster. What? Okay, can we break down just how much junk is floating around out there? Well, it's hard because there isn't any sort of worldwide monitoring system set up, and currents are always moving things around, but research from the National Center for Ecological Analysis and Synthesis and the Algalita Marine Research Institute pegs it to about 200 million tons of our trash in the ocean. There are about 75,000 pieces of plastic floating on the ocean's surface per square kilometer. That's not even counting the stuff that's underneath. 14 billion pounds, that's 6.35 billion kilograms of trash is dumped into the ocean every year. Recreational boaters dump about a pound every time they go out, but it's really industrial dumping that does the most damage. Merchant, military, and cruise ships. Merchant ships toss 5.5 million containers of trash into the ocean every day. There's also stuff like coastal sewage systems. About 1% of the trash floating in the ocean came from the sewers. And all that stuff gets taken out into huge currents called gyres that circle the world. The plastic floats around out there for, well, functionally for as long as we've had plastic. It takes about 500 to 1,000 years for plastic to photodegrade in the sunlight completely. And for that whole time, it's just breaking apart into smaller and smaller pieces that are floating around out there. And gyres have been carrying man-made trash all over, even washing plastic bags and other stuff up in Antarctica. And some of it is collected together, building solid hunks of trash over time. on. The Great Pacific Garbage Patch is a large system of floating trash islands, some of them as large as the deck of a sailboat. The total size is estimated to be anywhere from 700,000 to 15 million square kilometers. So anywhere from 0.5 to 8.1% of the total surface area of the Pacific Ocean. It's hard to say though, since most of it is right under the surface and hard to pick up on satellite imaging. That is a lot of trash, man. What do you do about all this trash? Nothing, unfortunately. Mostly nothing. See, a cleanup effort that would actually wind up picking up enough trash to start leveling the amount that we're putting in there out would take about 630 cleanup ships that could hold 226 million kilograms of trash each. That's about 20% of the size of the whole world's fleet of oil tankers. The biggest help, according to the conservation group Five Gyres, would be lowering the amount of plastics we use and throw away and letting the gyres wash what's already in the ocean up onto the shores and then cleaning up beaches and shorelines. But you can see why it's hard to find a single plane in there, I guess. Kind of weird downer news. I'm sorry about that. If you're looking for something a little more up, check out my friend Katie Wade's channel, Weird, Gross, and Beautiful, where she talks about animals she thinks are, well, weird, gross, and beautiful.
Wow.
That's a lot of trash. That's a problem that is difficult to solve. There is companies that are coming up with trash that with plastic that decomposes a lot faster than the plastic that we use now.
Like sun chips?
Sun chip
I
bags.
don't know.
They have that.
Sun chip bags have them? Yeah. So, you know, and often they'll decompose in water really quick. And if you can make it out of sugars, which can be done, they can actually make the bag itself out of sugar. And so when it gets in the water, it just decomposes. And of course, you want it to be a little tougher than just sugar. So there's some chemistry there, but it's possible that that's a fixable problem. What about dead zones? Okay, so everywhere on this map where you see a red circle, that's a dead zone of the ocean. And what is a dead zone? It's an area where the oxygen level is really low, the dissolved oxygen. Now, y'all been measuring this for the last several weeks. How much oxygen is in the water? Well, if that oxygen level gets below 2 parts per million, or grams per liter is what y'all are measuring, then we consider that not to be enough oxygen for fish to live. And we call it a dead zone, meaning you don't find hardly any fish living there. It's not just fish, it's all the other organisms we study too. They all need oxygen from the water. And why is that oxygen so little in these red areas? It's because what happens is fertilizer that we put on our land washes off into the rivers and is taken into the ocean. We're talking about nitrogen and potassium fertilizers, which is, if I want to go grow grass, I put a lot of nitrogen on the grass. I put a lot of phosphorus on the grass is another one. Put a lot of phosphorus, put a lot of potassium, and the grass will just grow like crazy. But what happens is the rain falls on your grass and washes that fertilizer into streams and rivers, and eventually it gets back in the ocean. And in the ocean, it causes the little phytoplankton. Remember phytoplankton? The little tiny microscopic green organisms we looked at, some of them under the microscope, the diatoms and things. They take that fertilizer and they grow like crazy. And you would think that would be a good thing to have these phytoplankton growing like crazy. But as it turns out, it's not. They grow like crazy, then they die, and their dead bodies are decomposed. And that uses oxygen. And it ends up using up all the oxygen in the water.
Yeah, that's what happened. Like, in the lake behind my house, we always have this thing where they come in and they kill all the grass, like the algae on top and stuff. And one time they did it wrong, and then it killed all the fish.
Ended up killing the fish probably because they didn't have enough oxygen.
Yeah, depressing.
So you can get giant fish kills, but usually what happens is the place slowly depletes of oxygen, and the fish just swim out of there, and you're left with a place with no oxygen, and that's less habitat for the fish, and it ends up being less fish. Yeah. Yes. So we have a problem with all those dead zones. And by the way, this is the scientific word, eutrophication. Eutrophication is a scientific word for too much nitrogen and phosphorus and potassium in the water. That means that's the scientific word for too much of that in the water, and it causes algae blooms and overgrowth. You want to see videos of dead zones?
Yes.
Heck yeah, you want to see videos of dead zones.
Yeah. Yeah. Yes. I think I got my dead.
Deadpool?
It's a little bit funky today. We've got the first of the fall storms kind of sweeping through. So we're just going to go out to about 50 meters of water.
Oceanographer Jack Barr has had plenty of bumpy rides off the Oregon coast, launching and retrieving these underwater gliders. From April to October, they gather data to help answer questions about the health of the world's oceans.
All right, but we're going to go with the swell. All right, here we go. Excellent. Ready? Now. The main things we're measuring are temperature, salinity, and importantly, the dissolved oxygen of the water. And that's what tells us how that low oxygen zone looks.
With National Science Foundation funding, Barth is studying low oxygen, or dead zones, which appear each summer off the Oregon-Washington coast.
So in 2006, we actually went to zero oxygen, and it extended many miles across the seafloor. And that's when we partnered with the Oregon Department of Fish and Wildlife to send a camera down on a remotely operated vehicle. And we got these images of dead crabs everywhere.
Worldwide, ocean dead zones now number about 400. Major man-made cause is agricultural runoff from rivers into the ocean. In addition, winds and currents move nutrient-rich but oxygen-poor water from the deep ocean to the coast. Microscopic organisms called phytoplankton thrive but then die, decompose, and the cycle continues. Climate change may also come into play.
We think there's two scenarios that global warming is potentially affecting this. So out in the deeper ocean, there's measurements that show that the oxygen levels are going ever so slightly down with time. When that water is brought to our shore, it's already low in oxygen.
Global warming may also be influencing wind patterns and changing ocean circulation. Barr says these smart robots provide new insight to understand our oceans.
To me, it's opened this whole new view under the sea. I think it's really revolutionized how we can keep a tap on what's going on out there.
For Science Nation, I'm Miles O'Brien.
That was also really good. You see, warm water holds less oxygen. Cold water holds more oxygen. So global warming doesn't help this situation where there's not enough oxygen. So all these problems kind of interact with one another. You've heard of overfishing. For 100 years, 200 years, 1,000 years, people fished and there wasn't any problem. But with our human population going up so fast, we're starting to see much fewer fish in the ocean, and one of the reasons is because we're catching them, overfishing. We tend to do this thing called fishing down the food web. What that means is we catch all the big ones, and after there are no more big ones left, we move to smaller and smaller fish. That's called fishing down the food chain. And they're keeping good count and good track of how many fish fishermen are catching, because it's a whole industry involved there. And
they really do give out big tickets.
we think now that there are only about 1/10 of the fish in the sea that there were 100 years ago. We've lost 90% of the fish, which is kind of unbelievable. Now, overfishing is not the only problem. There's all these other problems that are causing fish to have less numbers that we've talked about. But overfishing seems to be one of them, and so catch limits and things like that has really helped bring some fish from the brink of extinction. You can only catch a certain amount, and then you give the rest a chance to reproduce. I have a couple good videos on overfishing. This is called Shark Water. It's about overcatching sharks, and this is called The End of the Line. It's about overcatching fish, and if you want to rent them, you can get not rent them, check them out. You can get bonus points on quiz grades if they're low. But anyway, yeah, overfishing is a problem that we need to deal with. And another problem is introduced species. So one of the main things that can happen, do y'all know what ballast water is? Those big ships that you see out there, what they do to weight down their ship when their cargo hold is empty, they'll suck in a bunch of water. And that'll make the ship heavier so they don't rock around so much in the big waves. And when they suck up water, they can suck up organisms. There can be organisms living in that ballast water. And if the ship goes all the way around the world and releases its ballast water somewhere else, it'll introduce a new species into a new place that it's never been before. And often when that happens, that species has no predators and can multiply real fast and eat a lot of the species that are there that have never had to worry about this new predator before. And sometimes it's not a predator, it might be a little disease organism.
Little shrimp.
So introduced species can be a problem too. Read your section.